Okay. So the next and last colligative property that we're going to talk about is osmotic pressure. These are notes, I think they're called 13 end on Carmen. Whoa. Okay, so let's take a look at what's happening in this figure. We have a funnel that's essentially inverted and put into a beaker that contains water. Inside that funnel, we have a solution that contains glucose and water. Okay? On the bottom of the funnel, we put a semi-permeable membrane. And so this semi-permeable membrane allows some particles to go through and not others. In this case, it's going to allow water to transfer back and forth across that membrane, but it's not going to allow glucose to transfer. Okay? So if we sort of take a zoomed in look at what is happening on this membrane, okay, this yellowish line is representing that semi-permeable membrane, and the arrows are representing the particles crossing that membrane. And the small blue are the water molecules, and the purple ovals are supposed to be glucose. Okay, and you'll see with the arrows, only the water is transferring. With osmosis, a solvent, in this case water, moves from an area of low solute concentration to an area of greater solute concentration. So the solvent moves from an area of low solute concentration, CONC for concentration, to an area of greater solute concentration. Okay, there are thermodynamic reasons for this, which we won't talk about yet because we will get to those in a later chapter. Okay, so then what happens in the figure? So that we talked about the left side, we're going to now look at what's happening in the right. Our solvent molecules have moved into this funnel, and you'll notice there's a slightly lighter purple shade on this right side. That's supposed to indicate to you that the concentration of glucose is lower. Okay. The concentration has become lower because more solvent has moved into that funnel. Right? So then what the osmotic pressure refers to, and is shown by the symbol pi, is the amount of pressure that's required to go back to the original height, for instance, on this funnel. Okay? So how much pressure is required to push that solution back so it gets to its original height. The other way of thinking about it is it's a pressure that's required to stop osmosis. Okay, so the equation for osmotic pressure is, we're going to do uppercase pi equals I times uppercase M times R, the gas constant, times T for temperature. So again, I is just like it was before. It's our Van Hoff factor. Often with osmosis, we're thinking about larger molecules like proteins, sometimes sugars like glucose on the last example, things like that. And so in those cases, those are all non-electrolytes. I will be equal to 1. Okay. M is our molar concentration. So freezing point depression, boiling point elevation used molal concentration. We're back to using molar concentration, so moles per liter of solution. R, as I mentioned, is the gas constant, and it will be 0.08 to 1 liters times atmospheres over moles times Kelvin. Okay, so we have, notice in our units here, all that's going to cancel. We're going to end up multiplying R times the molar concentration. Molar concentration is moles per liter. We have liters per mole in R, so those are going to cancel. K is our temperature in Kelvin. That's going to cancel with our temperature. Okay, so we're going to be left with atmospheres, which is a pressure. That's good because we're thinking about osmotic pressure. Okay. Okay. So, if we solve this problem, what time are we at? 25. Let's work on this problem for maybe 2 minutes individually. All right. I think that you have all that you need here to solve this. Moles per liter. Yes. Take a couple minutes, talk with your neighbor, work on this problem, and then we'll come back and solve it together.
We have to use 0.798, so that's no sequence.
The equations, is that what you said? Yes, they have been in the past. I haven't seen the new equation sheet yet, but I would be completely surprised if they weren't on there. Yeah.
So no, because the 0.
It
Is
is.
it like a non-electrolyte, or is that not the
It's a non-electrolyte.
Are we supposed to know that for the exam, though?
I think that we are good about stating if it's an electrolyte or stating if it's a non-electrolyte.
Okay.
Who's it? Temperature has to be in Kelvin. Yeah.
Oh, wait.
Because it has to be able to cancel with the
You're probably right.
unit in R. All right, I'm hearing some good questions. A couple of questions that I would like everyone to make sure they know the answer to. Van Hoff factor for starch. This is a non-electrolyte, and maybe I should have been more explicit about that. Apologies. So I, in this case, is 1. And our temperature does need to be in Kelvin, okay, because it has to cancel out with the Kelvin in the gas constant in R, okay? So that's a good way to remember that. This is the R you're going to use for this chapter, okay? So given the information that we're provided, we have a temperature which we can convert to temperature in Kelvin. It'll be 298 K, 25 degrees C plus 273 to get the Kelvin. That's where that's coming from. Okay. So then the tricky part then is figuring out the molarity. Okay, and you're given grams of starch, and you're given a molar mass, and you're given a volume. And so if we find our molarity, we'll have to first find moles of the starch. So we'll have 0.798 grams of starch times this molar mass, which is 1 mole over 32,400 grams. So we're essentially dividing by the molar mass. Okay. And we get a small number here, 2.46 times 10 to the minus 5. Okay, so now we have moles. We need to find moles per liter. So we'll do 2.46 times 10 to the minus 5 moles over the total volume, which is 100 milliliters, so 0.1 liters. And we end up with 2.46 times 10 to the minus 4 for our molarity. Everyone agree? Okay. So then we can plug this value, our temperature, and I, and our gas constant R, into our equation for the osmotic pressure. So we'll have 1 for I times 2.46 times 10 to the minus 4 moles per liter times 0.0821 liters atmospheres over moles times Kelvin times 298 Kelvin. Kelvins cancel, liters and moles cancel, and we're left with atmospheres. And what did y'all get? 6.02 times 10 to the minus 3 atmospheres? Okay. Close-ish. Oh, I wrote 2, but let's say 3? I don't know. Never mind. Okay. Should be right. Questions on that? Yeah. Yes, you are definitely going to have an equation sheet. I will poke the people today to see when we're going to get access to that. I checked earlier on Carmen, it's not posted yet. But you should have all the colligative property equations, and you will get your constants as well. Okay. Okay, so here's a really good problem. This is like the highest level you're going to get in this chapter, okay? Make sure you know how to do this type of problem. And that is using a colligative property to find the molar mass of a solute. So here we're going to have a solution of an organic compound. And right now I'm going to write, because it's an organic compound, this is a non-electrolyte, I equals 1. It's prepared by dissolving 0.461 grams of solute in 100 grams of carbon tetrachloride. Okay, so we have a different solvent, not water this time. The freezing point of the resulting solution was lowered by 274 degrees Celsius, lower than the pure solvent. And then we want to find the molar mass. We're given our freezing point constant for carbon tetrachloride. All right. So here we have the equation we're going to use, our freezing point depression equation. Based on what we have in the problem, we know our K sub F is 29.8 degrees C per molal. We know the delta TF. It says that the freezing point was lowered by 0.274 degrees C. So that is the freezing, that is delta T. Okay. We know I is 1. And so what we need to find is the molality. Okay, that's something that we're not given in the problem. We were given, however, grams of solute and grams of solvent. All right. But those don't get us molality, right? And we don't have a molar mass. We're trying to find the molar mass. So let's first use our delta TF equation to solve for molality, M. Oh, let me actually just fill in some stuff here. Okay, we're going to rearrange our equation to solve for molality. M equals delta TF over I times K over F. We're going to have 0.274 degrees C divided by 1 times 29.8 degrees C per molal. If we look at our units, we have 1 over molal. So our units, when we divide this out, are going to be in molality. Okay, I'm doing the easy part for you. Where are we? Yes. We get 0.009195 for the molality. Okay. Everyone okay with that? Yes. Oh, you and this negative sign, everyone, me. Okay. Negative. Just, I hate that negative. It's not even necessary. All right. Yeah, you don't need it. You don't need it. It just doesn't need to be there. We're leaving it off, and we're taking this off. Was that your question up there? Okay. The way the problem is written is if you ignore the negative sign, you're good. The other thing you could have done is this. Oh, no, you're not given that. You would take if you had temperature of the freezing point of the solvent, Like if you actually had that value, minus, so you have, let's just say, what is freezing point of this? Is minus 5. I think this ends up being negative. I don't know. We're ignoring the minus. It's easiest that way. If you end up with a negative concentration, you've done it. You just take off the minus sign. You should not get a negative concentration ever, okay? All right. Okay, so that was supposed to be the easy part. Now we need to find the molar mass. We have molality. We have 0.009195 moles per, what's the denominator on molality? Kilograms of solvent. Okay, and our goal is to get grams per mole of solute. All right, take 2 minutes, work on that, see if you can figure out how to get to the molar mass. Oops. Remember that you're given mass of the solute and you're given grams of the solvent. How many people think this is easy? A couple of you, good. Okay. So, you know, we've got moles per kilogram of solvent right now for our molality. Our goal, like I said, is to get grams of solute per mole of solute. Because we know the mass of the solvent, and that's what's on the in the denominator of our molality, we can multiply by the known mass of solvent that was used. So is everyone okay if I convert that 100 grams to 0.1 kilograms? Okay. So we multiply 0.009195 by 0.1 kilograms of solvent. That's what was used. We're going to end up with moles of solute that are actually in the solution. So we get, I love zeros, so 0.0009195 moles. And we were given the mass of the solute in the equation, or in the problem. So we have 0.461 grams. That's what was used to make that solution. If we divide that by the number of moles which we've now calculated to be in that solution, we'll get its molar mass. We end up with 501.4 grams per mole for this organic compound. Okay. Yes. The last part or the whole thing? Yeah. Absolutely. This is like I said, this is the hard part, at least conceptually. So we used our freezing point depression to calculate molality. We had all of the other factors in that equation The only thing we didn't have was molality. So we use that equation to get 0.009195 moles of the solute per kilogram of solvent. That's the definition of molality, is moles of solute per kilogram of solvent. I always explicitly write that out so I can keep track of that. What we did when we made our solution is we put 0.461 grams of that solute into a beaker with 100 grams of carbon tetrachloride. Those are both in their beaker. Okay? So we know the mass of solute in the beaker. We know the mass of solvent in the beaker. Because we know that mass and we have our molality, we can multiply the mass of the solvent known by what we calculated for molality. So kilograms of solvent times the 0.1, which was in the beaker. That gives us moles of solute in the beaker. Okay? This is the moles of solute that are here. We know what that mass was from the problem, 0.461. So we can divide the mass by the moles to get the grams per mole. Yeah? So the question is, will you be told if something's an electrolyte or non-electrolyte? I think we've been really good about specifying if it's a non-electrolyte, especially if it's something obscure. All right. I think I have one more example of these that'll be in the notes if you want to take a look at that.